Right, now the second part, we are going to look at molar conductivity and Kohlrauschs law. Remember I told you we are still going to meet strong and weak electrolytes, as we are going to see later here. Now we are going to look at molar conductivity at infinite dilution, explanation of molar conductivity, Kohlrauschs law, application of Kohlrauschs law, and we conclude. Molar conductivity. Suppose we construct a cell having parallel plates 1 meter apart. The plates being of such an area that for a particular solution 1 mole of the electrolyte is present. So we're looking at a situation where we're trying to construct a cell having these dimensions. Now, according to William George Kohlrauschs, the molar conductivity designated lambda, capital lambda here, is defined as a conductance of a solution containing 1 mole of electrolyte placed between 2 parallel electrodes placed 1 meter apart. You see, this definition is very important. So we can see molar conductivity is given by capital lambda equal to this kappa, the specific conductivity we talked about, divided by concentration of the solution. Of course, where that K kappa is the electrolytic conductivity and C is the concentration of the solution. And remember we have said that this lambda, capital lambda here, is a molar conductivity. Now, molar conductivity at infinite dilution. The importance of molar conductivity is that it gives us information about the conductive ion produced by a solution by 1 mole of a substance. Now, experiments carried out on the variation of molar conductivity have revealed important results. We are going to look at them. Molar conductivity diminishes as square root of concentration is raised. Those with high conductivity, such as KCl and that, are called strong electrolyte. I said we are going to meet strong and weak electrolyte. And those with low conductivities, for example, acetic acid, are referred as weak electrolyte. Now, when we talk about infinite dilution, we should have in mind that we're talking about dilution to infinity. For instance, if you have a cup of tea that you have made, you want to drink that tea, and suddenly you pour that tea into a bigger cup, make up with water. Pour that into a bucket, make it up with water. Pour it into a tank and make it up with water. You find out that by the time you pour into a tank, there's every likelihood that you may not be able to notice the traces of your tea again in that tank. But that doesn't mean your tea is not there. It's there. You are diluted to the point that we say infinite dilution. That is very great dilution, that solution is very, very dilute. So molar conductivity of strong electrodes fall only slightly, and that of weak electrodes show very pronounced decrease with concentration. So when concentration changes, the behavior of strong electrolytes and the behavior of weak electrolytes are not the same in terms of molar conductivity. We are going to see shortly. Now look at these two graphs. We want to explain this molar conductivity. Look at this first one is for strong electrolyte, and this one is for weak electrolyte. This is our molar conductivity or molar conductance against concentration. The same thing is plotted there. We now use examples. Lanthanum chloride, calcium chloride, potassium chloride are all strong electrolyte. These 1, 2, 3 are strong electrolyte. Look at how their molar conductivity is varying. But look at acetic acid. Look at how the molar conductivity varied. For these 3 strong electrolyte, we can extrapolate just like we did here. Look at these dash lines here. shows extrapolation to the axis, to the y-axis, and that gives us molar conductivity at infinite dilution, as we're going to see. But here, we can extrapolate for this first line, this second line, this third line for lanthanum, calcium, and potassium chloride, but we cannot extrapolate for, acetic acid. Acetic acid is a weak acid, so the behavior is different from these three, strong electrolytes. So let's explain all these two diagrams here. Now, if we extrapolate the curves back to zero concentration, we obtain the quantity known as molar conductivity at infinite dilution or zero concentration. So when you dilute to the extent that the concentration becomes almost zero, that's what I mean by when you put your tea in a cup, dilute, put in a bucket, dilute, and then put in a tank. You have gone to almost zero concentration. That is infinite dilution. So when we extrapolate this, like I said, we get the molar conductivity at infinite dilution or zero concentration, which is also called limiting molar conductivity. And this time, we put a superscript 0 to differentiate it from molar conductivity. This is molar conductivity at infinite dilution. This is the value of molar conductivity when the ions are far apart that they do not interact or retard each other. So when it is very dilute, then the ions are very far apart. The extrapolation is only practical with strong electrolyte. Like I said here, you can extrapolate for these three electrolytes, but you can't extrapolate for this acetic acid, which is a weak electrolyte. For weak electrolytes, such as acetic acid, it's not possible to extrapolate. I've said that. And this is because the acetic acid dissociates more at greater dilution. Whereas when this happens for acetic acid, then we must have to look for an indirect method. Remember, for strong electrolyte, when we extrapolate, we will get molar conductivity at infinite dilution. But for weak electrolyte, we cannot get that. So we must look for an indirect method for determining the molar conductivity of weak electrolytes at infinite dilution. The increase, for strong electrolytes that are completely ionized at all concentrations, the increase in molar conductivity is not due to increase in number of these species. This is in fact due to the decrease in forces of attraction between the ions. So at higher concentration, the forces of attraction between opposite ions increases. Consequently, it affects the speed of the ions with which they move towards opposite charge electrode. This is called ionic interference. As the solution becomes more and more dilute, the molar conductivity increases until it reaches a limiting value, that is infinite dilution or limiting molar conductivity. That's the limiting value. This value is known as molar conductivity at infinite dilution. Said that. Now for weak electrolyte, ionic speeds are not affected by decrease in concentration. The increase in molar conductivity with increasing dilution is now because of, in other words, the degree of ionization increases for weak electrolytes. So increase in molar concentration in case of weak electrolyte is different from that of case of strong electrolyte. Because of that, we now have an indirect method of measuring the molar conductivity at infinite dilution for a weak electrolyte, and that is by using Kohlrauschs law. Now, Kohlrauschs explained all these observations in his law of independent migration of ions, which states that the molar conductivity of an electrolyte at infinite dilution is the sum of the molar conductivity of its ions at infinite dilution. So if you have sodium chloride, for example, and okay, let's say sodium chloride is not a weak electrolyte. So if you have acetic acid, for example, as a weak electrolyte, when it ionizes, you now get the hydrogen ion and the acetate ion. So in that case, Kohlrauschs is saying that the molar conductivity at infinite dilution for acetic acid is equal to the molar conductivity of the positive ion, the hydrogen ion, plus the molar conductivity of the acetate ion. That is the sum of the two independent migration of ions. Therefore, Kohlrauschs law suggests that at infinite dilution, molar conductivity of an electrolyte, for example sodium chloride, depends on independent contribution from sodium ion and chloride ion. Now, in general terms, we can now write this. This is the equation. This is the molar coefficient for positive, this is negative, and this is the molar conductivities for the ions. When we put all these together, we now get this equation. And that can help us to calculate the molar conductivity at infinite dilution for any other. And then we apply it, that's what I was trying to explain, to calculate the limiting molar conductivity of weak electrolyte. Now we may write this is HAC, which is equal to this plus HCl minus sodium chloride. So we have introduced sodium here. We have also introduced chloride here. If we subtract sodium chloride, what will remain here will be hydrogen ion and acetate ion. Therefore, we can still use numbers here or alphabets. Look at it. AD will be equal to AB plus CD. When we minus CB, what will remain will be AD, which is broken down in terms of ions here. That is what we use for the molar conductivities of weak electrolytes at infinite dilution. So that's the illustration. We have one here to calculate the conductance, specific conductivity. We have our equation here. So molar conductivity is given at this. A very simple example that you will understand. Thank you very much. We have looked at molar conductivity at infinite dilution, Kohlrauschs law, and application of Kohlrauschs law. So I hope to see you in the next class. Thank you.